Morning, everyone. I'm using this as a whiteboard so I can write things on. It's an old exam physics way. Um, Apologize for today. It's just my daughter's sick, and a student asked me to solve one of the homework problems. Where is it? It's right here, and that is chapter 8, problem 5. Chapter 8, problem 5. There you go. I think that's the one that I outlined in the classroom. So to solve for that, I need some calculator. Bring a calculator here. And so let's go for it. So we have a firework, but by the way, let me see if I can kind of outline the problem. So basically you have how do I annotate that? Just a second. I want to comment. Okay, good. Okay, so basically, you have a firework, right? It's going to be shoot with some angle, and it's going to go like this. Projectile motion, remember that. And then it said that when it gets to the highest point, it breaks in two fragments. One fragment and another fragment. Okay. And then it says that these two fragments are such that one falls straight down and the other fragments go somewhere, right? So we don't know. Let's say the first option is you don't know where the second fragment exactly goes. So put any direction. Can you see that? So it's just an explosion. So you have this first fragment going straight down, and this is given with an initial velocity 0 meters per second. 0 meters per second. Let me call this fragment number 1. This is fragment number 2. Okay, so there are two fragments, 1 and 2. So we don't know exactly what happened with this. We don't have a lot of information yet. But this is said that start out with an initial velocity 0 and falls straight down. Okay. And then let's read the problem. So we have a this initial projectile has 12 grams of mass. The initial velocity is given 65 meters per second, and the angle here is also given, is 80 degrees, right? Highest point separates in two pieces. So this fragment has a mass, so m, mass of fragment 1 is 9 kilograms, so therefore the mass of fragment 2 must be 3 kilograms, right? Separation up, but the 9 piece falls straight down, having zero initial velocity, I already put there, just after the explosion, neglect air resistance. And the first question is, at what horizontal distance from the starting point does the 9 kilograms piece hits the ground? So if you look at this little sketch, right? So we want to know how far from the initial launch this 9 kilograms fragment hits the floor. So basically you want to find this distance here, x for question A. Okay, so let's try to solve for that. So the first part you should be able by now to solve if you recall what you learn in projectile motion. So let's bring information and put in a table. So mass, how do I do this? Mass of initial mass 12 kilograms, initial velocity 65 meters per second, the angle is 80 degrees. I apologize if I go step by step, but I'm just trying to be as simple as possible. And this is the first part. So think about projectile motion. So in projectile motion, the angle of 80 degrees is given. And let me go back to our little design here. So in your projectile motion, your initial velocity must be projected in two components. The component in x is such that it never changes, and your initial velocity in the y direction changes all the time since the very beginning. So when you have projectile motion, you have to pay attention to the direction of your initial velocity. If the direction is other than the horizontal, you must project in x and y. The projection in x is such that will not change during the travel of your projectile, and the projection in y will be that of a free fall, which means as it moves up, it slows down to a point that when it hits maximum height, right? At this point, right here, the projected velocity in y is zero, as if the projectile had stopped in y. Okay, so let me go back to my little table and plug that information in here. So V naught x is equal V naught times cosine of the angle. And you know, in Excel I have to put this pi thing divided by 180. So here's my initial velocity in x. My initial velocity in y is equal V naught times sine of the angle. I have to multiply by pi because, by pi divided by 180 because, and something I did something wrong. So it's C3 times sine parenthesis D3, that's correct, times pi, put pi, it's better, pi. Oh, you know, when something goes wrong, it's better to start all over. Okay, can you accept what I want to do? Equal. Okay, start again. V naught times sine of the angle times pi divided by 180. Okay, so now I have my V naught x and V naught y. Okay, so with that information, I should be able to determine what is the range, what is the solution that is being asked for part A. Why? Well, remembering the projectile is intact up to this point, and then this point, one of the fragments falls straight down. So we want to find this distance here, and we can if we know the time. So let me find the time of the initial, and let me do something that's called initial part. The initial part is the one that goes from here all the way there. In the initial part, the time can be calculated how? How can we calculate the time? So let's go back here to our work area. Let me pull this down. So we can use, for instance, in the y component, V naught y and V final y and the time. And we have g. So we can use the equation of velocity as velocity in y change over time. So, and that is the final velocity in y is equal to initial velocity in y minus gt. Remember that? So final velocity in y is 0. And that is equal to initial velocity in y minus dt. So that after you do your little algebra and calculation and math here, you want to find the time is equal V naught y divided by t. Okay, so let me plug that in the Excel spreadsheet. So the time is equal V naught y divided by g, 9.81. Kaboom. So the time is this much in seconds. But if you find the time, so in projectile motion, we have two projections. Remember that? X projection, Y projection. So basically, all this information we developed here was pretty much obtained by using Y projection information. So in the X projection, the only thing we really have is the range, or the position as a function of that time is equal V naught X versus time. So we can take this time, multiply by V naught X, and have the solution of the first part. So let's do that. So the x as a function of time, which is in fact the solution to the first part, part A, is equal to V naught x times the time. And then we got 73 or something. It's right there. So that's the distance in meters, right? That's the distance in meters. Okay, so what else is being asked? Calculate the velocity of the 3 kilograms piece just after the separation. So now we have to go back to our work area and try to understand what happened as far as explosion is concerned. So this is the subject we are studying this chapter. There is an explosion. And if you think clearly, this is a situation that before explosion, there was no, you have a momentum, which is a particle is at the top point moving to the right with a velocity which is V naught x, because the V naught x is the same all over the path, and it doesn't have a component in y. Okay? It doesn't have a component in y. And after the explosion takes place, this is after the explosion takes place, you have exactly two particles one particle is going pretty much downward like this, right? And the other one, we don't know what happened. That's the second one. Okay? So let's apply conservation of linear momentum to this situation. So let's do that. Using conservation of linear momentum to this situation, before the explosion or before the collision, the total linear momentum is given by mass of the two fragments. They are together. They hadn't exploded yet, times the velocity that both of them had is v naught x. This is the momentum before. After collision, it's complicated because you don't know what happened with the second fragment. You know that one falls straight down, and I'm calling the fragment that falls straight down the fragment 1, right? So let's do that. So after, the total momentum after is equal to fragment 1 that falls down with an initial velocity that's 0, right? Velocity of fragment 1 right after, right? And which is initial in this case, is right after the explosion took place. And this is said by the problem to be equal 0. And this is in the y direction. And that's it. I don't have anything else for the fragment 1. There is only one component, and that component goes down. And the fragment 2, it should have two possible components. One is in x, and the other velocity component is in y. Right? But look at this. The momentum before was in the x direction, was horizontal. Therefore, the linear momentum after must also be totally in the x direction. So this component here must be 0. It doesn't have a projection in the y direction. So this is 0 too. Meaning that once the explosion takes place, the fragment number 2 flies not with an angle, but also in the horizontal direction with a velocity I'm calling v2 of the fragment 2 in the x direction. And this guy has a mass that we know. So let's plug that information in our table. So fragment 1 has a mass, and fragment 2 has also a mass. Fragment 1 has a mass. Let me see if I can find it. What is the problem? Fragment 1 has... Oh, shoot. What did I do? Oh, no, it changed everything. Oh, God. Okay, let me go back here. So it changed everything. See that? Sorry about that. So now the mass is 11. Mass is 11. The initial velocity is not 65, but 63. Okay, the angle is still 80 degrees. Okay, so here is the initial velocity, 69.2. Okay, so we got, again, that's the beauty of doing all these equations in Excel. You don't need to repeat anything. But now the 9 kilograms fragment goes straight down. So this is 9. So mass of the second fragment is 2, right? 2 kilograms. So that's the one that goes along the horizontal direction. What do we want to find? Calculate the velocity of this 2 kilograms piece. Oh, so if you look at your equations of conservation of linear momentum, right here. right? So let's do that. Using conservation of linear momentum, total momentum before v naught x, this is momentum before explosion, is equal m2 v2x, so that your velocity after is going to be equal to m total divided by m2, this times that much. So let's plug that in our equations. Okay, ratio of the masses times velocity, can't forget that. So V2 is equal rate of the masses, which is this, times the initial mass, times divided by initial mass times the initial velocity. I think that's what it is. Oops, it's all crazy. Wait a second, M2, let me see, did I plug the equations correctly? Oh no, the ratio, the masses have a different ratios. Okay, so I plugged my equations wrong. So this should be equal to this mass divided by this mass times this velocity, and then we get 60.2, all right? So 60.2 meters per second. And then after what horizontal distance from the starting point does this piece hits the ground? So basically, if you go back to your little sketch, and I apologize if I'm taking too long here, but now you have this second fragment. Where is my erasers? Right here. My second fragment is not going with an angle, but it's going like that, right? And then this second fragment is gonna go like in a projectile and fall somewhere here. And you wanna find what is this entire distance here, okay? So how do we figure the distance, the second fragment? Well, it's a projectile motion. You have the initial velocity, which is v2, right? The angle is horizontal. The time of the fall is the same, right? The time of the fall does not depend on, if there is no air resistance, depends not on mass, depends only on the height and g. The height is the same, so the time that it took the big fragments to go all the way up here is going to be the time that will take the smaller fragment to go all the way down. The time is the same. So we can use that information to figure the length. We can say the second segment, I'm going to call xb is equal to, I can use this, xb is equal to v2, which we just calculated, 60 point something, right, times the time, and this time is the same time that it took to go up, and we calculated here. Okay, so let's do that. So we go to our numbers. I don't want to miss that again. So the total, the final range is going to be equal. To the initial one, which we calculate somewhere here, which is this much meters, plus the velocity versus time. Oops. And you get a 40, yeah, we got something. And that's how you solve this problem. It has lots of steps, and I understand, so you have to use twice, in fact, concepts of projectile motion, and you have to be able to use conservation of linear momentum to interpret what happened exactly at the toppest part of the curve when the fragment explodes. All right? Hope it helped.